So let's continue the same track we were with handling distance. Let's say the person moves. Now we are including some more directions. Okay, we're going to say there's a north, south, east, and west. Right? So the person moves eastward 4 meters, and then he moves. Okay, so this is 4, and he moves southward. He moves again 4 meters. What's the distance traveled? The distance traveled is equal to 4 plus 4, which is 8 meters. Now, what's the displacement? Okay, now we are looking at vectors. Okay, there is an origin. The person displaces, his displacement is in the east direction, right? We represent vectors with an arrow, right? So this is how he travels his displacement 4 meters to the east, and then he does a displacement 4 meters to the south. So this is what is his final displacement. This is going to be his final displacement, right? This quantity here, I'm going to say OA. Okay, OA, the vector OA represents his final displacement. Now, how do you get OA? Okay, thankfully, in this particular case, we know that this looks like a right angle triangle, right? So we can apply Pythagoras theorem, and we can say that if this is 4 and this is 4, that means this should be root of the square, the sum of the square of the two sides. So this would be 4 root 2. That's the magnitude. What about the direction? So we say the direction, and we say theta, tan theta will be this side, by this side is 4 by 4, which is 1. So theta would be 45 degrees. Or you're looking at a southeast direction, right? So therefore, the displacement is equal to 4 root 2 meter in the southeast direction. Or you can say 45 degrees south of east. So you can see the difference when we use just magnitudes and we add it up. It was pretty simple. But the moment you're using vectors and you're adding up, yeah, you need to take the direction also into consideration. Now, suppose I made it slightly more difficult for you and said, okay, the person travels 4 meters straight, and then he travels, let's say 30 degrees. This is 4. This is 4, right? He takes a left turn. He goes in the 30 degrees south of east. He travels another 4 meters. What is the distance? Simple, it's 8 meters. What is the displacement? Okay. Now we are looking at a displacement. We fix this as the origin, and we are looking at a displacement somewhere like this. And we have to calculate this. And this is not a Pythagoras right angle triangle. It's going to get more complicated. Well, welcome to the world of vectors. Vector algebra, or the stream of math of vectors, okay, the language of vectors, helps you solve these quantities of physics, helps you work with these quantities of physics which are vectors, right? It makes it simple. And that's why this branch of math called vector algebra is important to us for physics, because physics, as I said, is best expressed in the language of math. Okay? And vectors, quantities in physics are best expressed because you need to add these quantities, you need to subtract these quantities, you need to multiply these quantities, you need to divide these quantities, which are vectors. And vector algebra is going to allow you to do that elegantly, easily, simply, right? And that's why we're getting into the world of vectors, understanding how do you add vectors, how do you subtract vectors, how do you multiply vectors, and how do you, okay, we don't get into division of vectors. That's for another day. Once again, before we leave, a reminder of some of the scalar quantities that we come across. We've already come across scalar quantities, which was distance, speed. You can also say energy, pressure. What about vector quantities? We already saw displacement, we saw vector, we have acceleration, Other than that, we have our other vector quantities could be force, and probably something like angular momentum, right? Could be a vector, or an electric force could be a vector, right? So scalars and vectors. So welcome to the world of vectors.